will be PhD student Hanchen Wang, who will present his project 3D deep learning for large-scale point cloud process. So Hanchen, are you here?
Yeah, I'm just share my screen. Can you see it?
So thank you for coming, and you are welcome to start your presentation.
Okay, so yeah, so my proposed topics for the CAPA award in last year it's called 3D deep learning for a large scale point cloud process. And so basically, a very short introduction is what is a point cloud. So essentially, a point cloud is a set of points that has been separated or located in the space. And it can be collected through devices such as LiDAR, which is widely used, which is a widely used data collector in the autonomous driving, and the depth camera, which is well, it's kind of largely used in the gaming industry to record the motions of humans, and it can be also converted from the other formats of the objects in the computer graphics, such as mesh or voxels, as well as depth map, 2D depth map. So you can see that our point cloud has variable, lots of resources in the collection, as well as a lot of as well as can be converted from lots of other object types representations. And so towards building up large-scale point cloud, towards building up a large-scale point cloud deep learning model, we're kind of want to solve this question by
Hanchen, would you like to put on the full screen, because your screen size is a bit small?
Okay. Share full screen. How about this?
Yeah, that's better.
Okay. So we're want to tackle this problem by propose some strategies for unsupervised pre-training for deep learning models on point cloud. So unsupervised pre-training is widely used in deep learning these years for dealing with data such as language, graph, and of course, and we want to use it for point cloud. And for the language, you might heard of BERT or recent or GP3, especially famous in last year. So for GP3, there's a large web engine, and you can type a few sentences, and it can help you like complete the entire paragraph of your sentences, or potentially have a dialogue with you that is automatically generated by the trained GP3 model. And this is so unsupervised. It stands for that we don't need to provide labels for the training data. And the pre-training is like we propose generalized auxiliary tasks that can be used to pre-train the model, and the pre-trained model can be shown that to be better or faster to converge and to be to have improvement on several downstream tasks, such as classifying an object, such as segmenting a thing, parts of the thing into a class, such as you segmenting indoor point cloud scans into classes such as ceilings, tables, chairs, etc. And so to be more specific, our method can be has a diagram like this. So for our original 3D point cloud, we first to randomly select some camera viewpoints, And we use this camera view points along with an algorithm called Z buffering to generate a few occluded point cloud. And after that, you train a completion model, a deep completion model that takes the occluded object as input and outputs and complete the shape of the point cloud. And this completion model can be later used for different downstream tasks, such as classification and segmentation. And so now let's show some results of this pre-training. So the pre-training is about to complete uncompleted shapes and of the 3D point cloud. So the very left column is the input of our completion model. So it's a part of the object. So as the example shown at the left, it's a cup, and our model output the complete shape in 2 steps. It first complete it's in a coarse, it ends into a fine style. And the second column is the cross output of the completion model. And the third is the fine output of the completion model. And this last column is we call ground truth, which is the shape that we use to generate this self-occluded objects. And for the right half, it's another example. So I think this is the example of the sofa, I think, yeah, or coach. And the input is a part occluded sofa, and our completion model can successfully learn to complete the entire shapes, giving a part observations of the point cloud object. And there's some more examples. So now the left one is a bottle, and the input is a half or a bottle. You can also think it as a bottle that you observed from a very specific viewpoint. And the right example is kind of bottle or vase. So it's you can see that our model can learn to complete the shapes for various object classes. But also we have some failure examples for the completion pre-training. So you can see that for the left example, it's a chair, but it has a bit artistic style for its leg. So you can see that our model can successfully recognize this object as a chair. Since the completion results, it still we can visually see that it's a chair, but it failed to capture the fine details of the object. For instance, it recognizes it's a chair, but it did not successfully show that it has this kind of shape. And the right example is similar. So we can see that the model can successfully recognize the table, but it fails to complete its legs, its support parts. So it's a very common which is for like structure instead of the provided ground truth shapes. But yeah, so we show that even the failure example, our model can still capture that which class this object belongs to, but might not be always successful to complete the fine structures of that object. And we show some empirical results on the downstream tasks. So a very basic task is called classification. So classification task is about given a 3D point cloud, the model needs to predict the object class for that set of points. And we want the model to be as precise as possible. So we want the accuracy on the test set to be as high, as close to 100 as possible. And so the right upper hand is an overview of the dataset we use. One of the dataset we use to benchmark this baselines and with other pre-trained methods. And it's basically called ModelNet 40, which contains 40 different object classes and in a total of 8,000 objects. It's the first rows in the table. And our pre-training method is called OCO. So it stands for occlusion completion. And the RAND stands for random initialized. So it stands for your random initialize the weights of the entire deep networks, and you train them from scratch. And the Jigsaw is previously very famous pre-training method with PointScout. And we show that there's 3 different object classification data set. And under 3 different model, 3 different baseline models that such namely PointNet, PCN, and DGCN. We show that our pre-training method has a better test accuracy, better test performance in comparison to previous method and random initialization on this classification task. And we're also doing more specific settings for classification task, which is called few shot. So few shot means your training sample, the number of your training sample is extremely small. So for a 5-way 10-shot, which means for each class of the 5 provided class, you only have 10 objects for the training, and you need to test your model on the entire test set. So you can think of it a bit, it's a quite challenging setting still in the classification tasks. And we show that in the few shot setting, our pre-training model, which is the last row called DG7 OCO, and the row called PointNet OCO has better test or comparable test performance in comparison with a few others pre-training method, and it's outperforms all the baseline models that with random initialization. And next downstream task is about called semantic segmentation. So basically, given a scan of the indoor scenes of 3D points cloud, the task is trying to predict which semantic class, which object class that points belong to. So, for instance, for this diagram, it's a scan of a kind of a meeting room, and you can see that the deep blue colors stands for kind of the floor of the meeting room, and the red stands for the chairs. The purple kind of stands for tables, and the green stands for the whiteboard. So this is basically a diagram, visualization of what this data looks like, and what we color them by their labels, by which class it belongs to. But in training the model, we only have the coordinates of the points, and we show that for this specific task, which have over like 24 rooms in total, our model, our pre-training method can still outperform the previous method in the different for all the different baseline models. And we also apply this on a very large scale outdoor point cloud data, which is so part of them is collected from Cambridge by a team in Oxford, and So we still it's very similar to the indoor semantic segmentation, but instead the object class might have different sets. So the object class is now become ground vegetation and building and etc. And our model still can outperform the random initialized baseline models in terms of the overall test accuracy and the mean intersection of unions over all the classes. And the last result I want to show that is the learning curves. So towards to do a large scale point cloud processing, a very common benchmark is called is to show that your model can converge faster or converge better in terms of provide an efficient and effective solutions for processing large scale point cloud. So in this 6 small figures, we basically show that our proposed pre-trained method called OCO can for different baseline models and under various tasks, it can converge a bit faster as well as higher in the test accuracy in comparison with other randomization method and the pre-trained method. So this is basically the main results of our work on proposing a pre-trained model for processing large-scale point cloud. Thanks for listening.
Thank you very much. So Hanchen, and I would like to open the floor to any questions. Anyone would like to ask something?
Where do you, so yeah, this has been done for a sort of bunch of applications in different groups around the world. Where do you see this being used for in your research? In the next 5 years, how will you use this in your research?
So essentially, we proposed a method, and this pre-trained method is potentially can be used for the model that is also going to be proposed in the next 5 years. So we proposed a method that can be used for pre-trained point cloud models, not necessarily to be the existing ones, but also for the potentially emerging ones. So if people are saying this pre-trained model is useful, they can use it as a better initializer for their proposed models instead of to initialize from random distributions. And I think this will be useful for the upcoming point cloud models in the future.
Okay, thank you.
Thanks.
Any more questions? Yes. If not, then we would like to thank the speaker. Thank you very much, Hanchen.